this straight line on the blackboard. But if I'm using curvilinear coordinates, for example, spherical polar coordinates, then there's a curvature to these coordinate lines. That curvature introduces into the straight line equation things like 1 over r or r squared. And if you write this equation in curvilinear polar coordinates, you end up with 1 over r something sine theta plus whatever. And it's just a straight line. But that's because these things are curved. Okay? And those things, this 1 over r's and the r square, are all expressions of the connection of the space. An interesting thing, what are these 1 over r's? They come from the fact that, of course, we have this angular thing over here, right? What is this a measure of? It turns out to be a measure of the curvature of these curvilinear coordinate lines, right? The theta and phi lines are circles, right? What is the curvature of a circle? It's defined as 1 over r. The larger the circle, the larger r, the less curved it is, the more it seems. So it's like the Earth's surface seems to be flat because r is very, very big. It goes as 1 over r. The curvature goes as 1 over r. The smaller the circle, the more you'll notice the curvature. Okay? So it's inversely proportional to r. This curvature, right, it's a measure of the coordinate line curvature. And in differential geometry, that's the connection. The connection, now we'll talk a little bit more about, I kind of hinted at it before. The connection is a set of quantities in any space that tells you how things are curving. Okay, just not to put it non-technically, right? How things are curving. If you have curvilinear coordinate lines in a flat space on a flat surface, you know that your geodesic equation, for example, is going to look funny. It's going to have sine thetas and r's in there and so on and so on, even though it's a straight line. If you use Cartesian coordinates, it will simply be x double dot equals 0, or y double dot equals 0, z double dot equals 0. If you're going to use r theta phi in a flat surface on a flat space, you're going to get r sine thetas and so on popping in there. All right, because your coordinate lines are curved. The connection also tells you on a curved surface. If you draw the straightest possible line on a curved surface, even though it's a straight line, the surface is curved. There are going to be functions creeping into the equation of the geodesic. Even if you use Cartesian coordinates, x, y, and z, right, you're going to find that you can't write x double dot is equal to 0. You're going to get x double dot y plus y squared. I don't know. Something is going to happen here. You can't write just this on a curved surface. And if you use even curvilinear coordinates, r theta phi on this curved surface, you're also going to get r squared sine theta squared. You're never going to get just, you know, x double dot equals 0 or y double dot equals 0. And in a curved space, the same thing happens, of course. You can't get away from having these other functions pop up. All right? So the connection is that mathematical quantity that tells you how that happens, so that you can write the equation. For example, the straightest line equation that tells you, okay, put this in front of the x, and put this in front of the y, and put this in front of the z. All right? And one of the components of the connection, even in a flat space, on a flat surface, if you're using curvilinear coordinates, is this 1 over r thing, which comes in very simply from the curvature of these coordinate lines. And it then manifests itself in the divergence. This is really like an r theta, this 1 over r. It has nothing to do with time. This is the curvature of this coordinate lines in a flat space and so on. Okay, so r theta over here. Gamma, this one will be the r phi.